Welcome, everyone. Today, we are diving into the fascinating world of electrical circuits and devices, specifically focusing on Boolean algebra. This is the mathematical foundation that allows us to analyze and simplify digital logic circuits.
Before we look at the specific laws, let's set the stage. Boolean algebra is unique because we only ever deal with two states, 0 and 1. Despite this limitation, many rules from standard algebra still apply. A key thing to remember as we move forward is our terminology. When we talk about multiplication, we are referring to the logical AND operation, which we call the product. When we talk about addition, we mean the logical OR operation, known as the sum.
Think about standard multiplication. 9 times 10 is the same as 10 times 9. The commutative law in Boolean algebra works exactly the same way. Whether you are using an AND gate or an OR gate, swapping the order of the inputs does not change the final output. A and B is identical to B and A. Next is the association law. This applies when you are chaining together multiple operations of the same type. If you have 3 inputs going through AND gates, it doesn't matter which 2 you group together first. Grouping B and C, then ANDing with A, gives the exact same result as grouping A and B first. The same principle holds true for OR gates. The distribution law should look very familiar if you've ever multiplied out brackets in standard math. The AND form is straightforward. A ANDed with the group B or C distributes to A and B or A and C. Interestingly, in Boolean algebra, this also works in reverse for the OR form, which is a bit different from standard algebra, but incredibly useful for simplifying complex logic. Now we get to a rule that is highly specific to Boolean logic, the absorption law. If a variable appears both outside and inside a bracketed expression, it essentially absorbs the other variable. For example, A ANDed with the group A or B just simplifies down to A. This is a powerful tool for eliminating redundant logic gates in a circuit. Here is a cheat sheet of other essential identities. Some are highly intuitive, like double negation. If you invert a signal twice, you're back where you started. The idempotent law tells us that ANDing or ORing a variable with itself just yields the variable, and the annulment law shows that ORing anything with a 1 guarantees a 1 output, effectively overriding the variable. Let's put these rules into practice. Imagine we have a messy expression derived from a circuit. By applying our laws step by step, we can drastically reduce it. First, AA becomes just A using the idempotent law. Then we can use distribution and absorption to eliminate the redundant V terms. What started as a complex 4-term expression simplifies beautifully, meaning we can build the same circuit with far fewer physical gates. Now, for one of the most famous tools in digital logic, DeMorgan's theorems. The easiest way to remember this is the rhyme, break the line, change the sign. If you have a long inversion bar over an OR operation, you can break the bar into individual inversions and change the OR to an AND. This proves that a NOR gate is functionally identical to an AND gate with inverted inputs. So how do we get these algebraic expressions in the first place? We often start with a truth table. If we want to design a circuit, we look at every row where the desired output is a 1. We write a min term for each of those rows, where a 0 input is inverted and a 1 input is normal. Adding all these min terms together gives us a sum of products expression. Alternatively, we can focus on the zeros. If we look at every row where the output is 0, we can create max terms. The rule here is flipped. A 0 input is written normally, and a 1 input is inverted. Multiplying these max terms together gives us a product of sums expression. Both SOP and POS describe the exact same logic, just from different perspectives. Because max terms are simply the exact opposite, or complement, of min terms, we can easily convert between sum of products and product of sums. How? By using DeMorgan's theorems. If we take a min term, apply an inversion bar over the whole thing, break the line, and change the ANDs to ORs, we perfectly derive the corresponding max term. To wrap up, Boolean algebra is your toolkit for taking complex, messy logic requirements and simplifying them into elegant, efficient circuits. By mastering laws like absorption and DeMorgan's, you can save hardware, time, and money in circuit design. For your next steps, I highly recommend researching how these Boolean principles apply to specific combinational components, like binary decoders, encoders, and multiplexers. Thanks for watching!